Okay, welcome back to our algebraic graph theory seminar. And today, Bidi is going to tell us about the intersection density of transitive groups of degree 3p.
Okay, thank you very much for inviting me to give this talk here. So I'm going to talk about the intersection density of transitive groups of degree 3p. But in general, I want to talk about this degree here in a more general way. So this is joint work with Razafimahatratra from the University of Primorska, Angelo Biagin from Technion, and Karen Marr from the University of Regina. Okay, so let us first start with the EKR theorem, the Erdos-Corrado theorem. So this was proved in the 60s by Erdos and Rado, and it states that if you're given two positive integers, n and k, such that n is greater or equal to 2k plus 1, and if f is a collection of k subsets of the first n positive integers, so I'm going to start denoting the set by this, such that for all a and b that you take in the collection, they are not disjoint, then the size of the collection is at most n minus 1 choose k minus 1. And equality holds here if and only if f is of this form. So what you do is you take a certain a in n, and you take all the subsets of n of size k that contains this element a. So somehow these are the most obvious examples that attain this bound, and the Erdos-Corrado theorem says that these are the only ones, in fact. So this can be extended easily to transitive groups. So if you are given a finite transitive group, so here we have a permutation group acting on omega. So omega, the number of elements in omega is called the degree of the group. And by transitive, I mean that if I take two elements of omega, there is a group element in G that maps one to the other. So if I'm given a subset f of G, then I say that this is intersecting for any two permutations, here sigma and pi that I take in F, there is an element of omega on which the two permutations agree on. And one might ask in this setup, so what's the obvious intersecting set? So this is going to be the point stabilizer and its coset. So what's point stabilizer of my group G? So say I take this omega and I take all the permutations that fix this omega, another type of intersecting set. Obvious intersecting set is if you take, say, omega and omega prime from omega, and you take all the permutations in G that would map omega to omega prime. So this is a coset of a stabilizer of a point in this case, and these are the examples of obvious intersecting sets. And the intersection density of my transitive group now is the rational number given by the following. So I'm going to denote it by rho of G. And it's the maximum of these ratios where f is an intersecting set in G, and this G omega is the point stabilizer. So this is the stabilizer of omega, in fact. So the maximum over all of the intersecting set. And note that the intersection density of a transitive group G is always at least 1. This is because this G omega itself is intersecting. So you always have a 1 in this set. And for those transitive groups for which rho of G is exactly equal to 1, I'm going to say that they have the EKR property. And I say that G has the strict EKR property if whenever I take an intersecting set in G with maximum ratio, so it attains the ratio given by the intersection density, then F has to be a coset of a stabilizer of a point. Okay, so let us see some examples. So if you look at the symmetric group in its natural action on the first n positive integers, for instance, then this has the EKR property and the strict EKR property. The EKR property was proved by Deza and Frankel in the late 70s. The strict EKR property was proved independently by Lahoz, Malvenuto, Cameron, and Koo in 2004. And in 2009, there was an algebraic graph theory proof given by Godsil and Marr of these two facts. If you look at PSL2Q in its action on the projective line PG1Q, then this has the EKR property and the strict EKR property. But for instance, if you replace these two here by 3, then this group has the EKR property, but not the strict EKR property. And in general, well, when n is greater or equal to 3, this happens. And if I take the permutation group that corresponds to the group action of the alternating group alt4 in its action on the cosets of this cyclic group C2, then this has intersection density equal to 2. So this one doesn't have the EKR property nor the strict EKR property. And one of the most general result in this area is due to Marr, Spiga, and Tep from 2015. They showed that if you are given a finite two-transitive group, then you always have the EKR property. So what's a two-transitive group? So it is a group that is transitive on omega, but at the same time, it is also transitive on the set of all distinct pairs coming from omega. And so most work on the intersection density of transitive groups focus on a study of specific families of groups, such as the symmetric group, the alternating group, PSL, NQ, and other classical groups. So we would like a more general result, similar to what Marr, Spiga, and Tep did. So here, the result depends on this two transitivity. So we would like something like that, maybe based on the rank, transitivity, or the degree, or any other parameter. So in this talk, I'm gonna focus on the degree, so the number of points that my transitive group acts on. So for any n greater or equal to 2, we can define the following set, In, which consists of all the possible intersection densities of transitive groups of degree n. So in other words, the number of points that this group acts on is n. And of course, this depends drastically on the choice of this integer n. So for instance, when n is equal to 18, we are still not sure what this set is exactly, because some of the groups of degree 18 are just too big to even check on the computer. So this drastically depends on the choice of this n. Okay, so now how do we prove these types of results? So we use graph theory to prove this kind of result. So if you are given a transitive group G, a derangement in my transitive group is going to be a fixed point free permutation, so a permutation without fixed point. And let der of G be the set of all of these derangements of G. And the derangement graph that we are going to denote by gamma G is the Kelly graph of your transitive group G, and the connection set consists of all of the derangement of the group G. And so this is a graph whose vertex set is G, and two group elements G and H are adjacent if and only if this product is a derangement, so a fixed point free permutation. So for instance, this is the derangement graph of the dihedral group of order 8. The red vertices are the rotation, and the blue vertices are the reflection in your dihedral group. And so you just look at these types of product. If it's a derangement, then you have an edge. If it's not a derangement, then there is no edge. So why are these graphs important in the study of intersecting set in this case? So it's because of the following equivalence. So if you are given an intersecting set in G, then it's not hard to show that, in fact, this is a co-collinear derangement graph or an independent set in the graph. And the converse of this also holds. So if you have a co-collinear derangement graph, then it is an intersecting set in the group G. And now it's not hard to show from this equivalence that your intersection density, in fact, is nothing but the independence number of your derangement graph divided by the order of a point stabilizer. And since my derangement graph is a Cayley graph, so it is a regular graph, of course, but it's also transitive. It's also vertex transitive. So I can use some techniques on these kind of graphs to give an upper bound on this this independence number here, since our problem now is reduced to a graph theory problem. So namely the click-co-click bound, and another bound that is often used is the Hoffman's ratio bound, or a weighted version of it. So what's the click-co-click bound? So it's the following. So if you are given a vertex transitive graph X, so vertex transitive means that if you look at the automorphisms or the set of all symmetries of your graph, then it acts transitively on this on the set of vertices. If you have this, then this product, this inequality is satisfied. So the size of the maximum co-click in your graph, which is alpha of X, multiplied by the size of the maximum clicks in your graph, which is omega X, is at most the number of vertices. And it's not hard to show using this that, for instance, if you're given a prime P, then the set I of P is, it just consists of one. So in other words, all transitive groups of degree a prime number have the EKR property. Their intersection densities are all equal to 1. How do we prove this? The proof is very easy. So if you are given such a group of prime degree P, then by transitivity of the group, P has to divide the order of your group. Using Cauchy's theorem, you can find an element in your group that has order P. And if you look at this, the subgroup generated by this element G that you have here, this corresponds to a click in your derangement graph of size P, and this is of maximum size here, in fact. And using the click-co-click bound, one gets that the independence number of gamma of G is at most the size of G divided by the order of the elements here, so divided by P. And note that this G divided by P here is exactly the order of a point stabilizer. So if you put this the other side, then you get exactly the definition of your intersection density. So the intersection density here is at most 1. So this is equal to 1. So that's how this is proved using the click-co-click bound. If you look, for instance, at groups of degree 2p, where p is an odd prime, then you can also prove some interesting result using the click-co-click bound. So recall that an Mn semi-regular element is a permutation which is a product of M cycles of length n. And it's not hard to show that if you are given a transitive group of degree 2p, then there is always a 2p semi-regular element. So in other words, a permutation that is a product of two cycles of length p. And it's not hard to show as well that whenever you have this, the subgroup generated by this will give you a click of size p in your derangement graph. And using the click-co-click bound, one can bound the intersection density of G like this, so it's between 1 and 2 for all transitive groups of degree 2p. So I had a conjecture in one of my papers that, in fact, this intersection density here is just 1 or 2. And this is what Marušić, Judurović, Kutnar, and Miklović showed in 2021. So I of p is always equal to 1 or 2 for any odd prime that you take. And if you look at now, if you look at the transitive groups of degree a prime power and I of pk, where k is greater or equal to 1, is also it only consists of 1. So all transitive groups of degree a prime power have the AKR property in this case. And this was proved by Marušić, Judurović, Kutnar, Miklović independently, Lee Song, and Pantangi in 2021. So now I want to talk about the main result of the talk. So we start with a conjecture that Karen Marr, Pablo Spiga, and I had in 2021. So the conjecture is as follows. So if you're given two distinct odd primes, P and Q, then we conjecture that I of PQ is in fact just 1. And one can note the following first. So Marušić showed that if you are given a transitive group of degree m times p, where m is any integer that is lesser or equal to p, then you can always find an MP semi-regular element in this group. So in other words, a permutation which is the product of MP cycles. And using the click-co-click bound, again, it's not hard to show that the intersection density here is at most Q using these semi-regular elements. And probably we should have phrased this question. Sorry, we should have probably phrased this conjecture as a question instead of a conjecture, because there is a transitive group of degree 33, number 18 in the library of transitive groups in GAP and SAGE that has intersection density equal to 3. And in fact, in 2021, Marušić, Judurović, Kutnar, and Miklović showed that if you are given an odd prime P that is of this form, here this fraction is a prime number. If this is a prime number, then Q has to be a prime number as well, and N is also a prime number. So if you are given such a prime, then there exists a transitive group G of degree P times Q, whose intersection density is equal to Q. And in addition, it also has the property that omega has a unique G-invariant partition. So I'm going to talk about the second part later, but let us see how they constructed this counterexample to our conjecture first. So they used the so-called linear code in this case, cyclic code. So what is an MKQ linear code? So it is a k-dimensional subspace of FQM, so an m-dimensional vector space over FQ. And an MKQ linear code is called cyclic if it is invariant on the cyclic permutation of the entries. So my entries, these are vectors. So if I cyclically permute the entries, if that remains in C, then my code is called cyclic. The Hamming weight of a code word C that I take in my cyclic code is the length of the code minus the number of zeros in my code word or in my vector, if you prefer this. And Marušić, Miklović, Kutnar, and Judurović constructed a PKQ cyclic code C for every projective prime P, which is of this form. So a prime number is called a projective prime if it is of this form. And the reason for the word projective is because this number is the number of points in a projective space. So if you have such a prime, then they constructed a PKQ cyclic code C with the property that the Hamming weight of each code word that you take in your cyclic code is exactly Q to the K minus 1. And this is not too important here, but the important thing is that this Q to the K minus 1 is strictly less than P in this case. So they constructed this cyclic code, but how did they get the permutation group of degree PQ from this? So this is their construction. So for any code word of this form that you take in C, one can define the following permutations. So beta C is from ZQ cross ZQ to itself, and what it does is it takes ij to I plus the jth entry of your code word and j on the other component. And alpha is the permutation that will take ij to ij plus 1. Okay, so if you take the subgroup generated by all of this beta C here for all of the code word in C, and if you take GC the subgroup generated by HC and this permutation alpha, then this gives you a transitive group, but it is also in primitive, in fact, of degree PQ. And this is the group that has intersection density Q here. One of the maximum intersecting set in this is this subgroup HC. And basically, what's important here, how do you show that, in fact, this is intersecting? So what you do is you can just show that this beta C, in fact, has a fixed point. Why does beta C have a fixed point for any C in C? Basically because of this property here. So the Hamming weight is at most P minus 1 in this case, which is P is the length of the code here. So when you look at this definition from this viewpoint, then the number of 0 in each code word should be at least 1. That's the meaning of this here. So if you take a C in here, there is at least a 0 in one of these entries then. And so for that particular entry, if you replace that here, then you have a fixed point, in fact. So that's what they did here. And yes, so this can be used as long as the Hamming weight of each code word is strictly less than P. And some examples. So if you look, for instance, at 13, it is a projective prime. So there exists a 1333 cyclic code C with the desired property, which is the Hamming weight is at most 12 in this case, but here it's constant. They are all equal to 9. So there is a transitive group of degree 39 that has intersection density equal to 3 in this case. But the interesting thing is that this also holds even if the prime number is not a projective prime. So 11 is not a projective prime in this case, but there is a cyclic code with parameters 11, 5, 3, but whose Hamming weight, the Hamming weight of each code word is at most 11. So this gives you a transitive group of degree 3 times 11, so 33, that has intersection density equal to 3 in this case. And so I of 33, using the computer, it's not hard to show that I of 33 consists of just 1 and 3. And for I of 39, it contains 1 and 3. So this was the construction that disproved our conjecture. So I was still, after this, I was still interested to study this problem. So the question is, what about the transitive groups of degree PQ? And what are the elements of this set I of PQ? So one can check on the computer that I of 15 and I of 21, for instance, it's just 1. And we saw earlier that I of 33 consists of 1 and 3. So people who worked in this area, including myself, were thinking that maybe if you're given a transitive group of degree PQ, then your intersection density is 1 or Q. But this, again, turned out to be false because there is a transitive group of degree 39, number 59 in the library of transitive groups in GAP and SAGE that has intersection density 3/2. And there is, again, a cyclic code behind this group. So there exists a 1363, so it's 6-dimensional here. Cyclic code C with the property that the Hamming weight is at most strictly less than 13 for each of the code word. And if you look at the permutation automorphism of the code, so this is basically the set of all permutations that maps a code word of C to itself by permuting the indices of the code words. So the permutation automorphism of the cyclic code here is the semi-direct product, which is the dihedral group of order 26, in fact. And this is the transitive group that gives rise to this this intersection density 3.5 in here. So it's this group 3956. And basically, this is the permutation automorphism of the code. And here, this is coming from the dimension, so F3 and 6. And when I showed this this group to Karen Marr, so she jokingly asked the following question. So for any transitive group G of degree 3 times P, where P is an odd prime greater or equal to 5, is it true that the intersection density of G is 1, 3.5, or 3? And this is the main result of this talk. So basically, this result is most likely true. So with Rogayemadeki, we showed the following. So if you have such a group, then if your group is primitive, then the intersection density is 1. If it is imprimitive and quasi-primitive, then the group is an almost simple group that contains a PSL NQ, and P has to be a projective prime. And if your group is non-quasi-primitive, then the intersection density is what was asked here. So rho of G is one of these, or P is a Fermat prime. So I'm gonna give a sketch of the proof of this for the rest of the talk. Okay, so we start with what the hierarchy of transitive groups. So a G invariant partition of omega is a partition that has these properties. So if you take B in your partition and G in G, then one of these two situations happen. And if you're given such a partition, then there is an induction of your group G on the partition, and we're going to denote that by this G bar subscript the partition. And this is how I like to view this the transitive groups. So you first of all have the quasi-primitive groups. So these are the families of transitive groups with the property that whenever you have a non-trivial normal subgroup, then that group is transitive. This contains the primitive groups. So these are the transitive groups with the property that they're only G invariant partitions are trivial. So in other words, the part of your partition either has size 1 or it's the whole thing, which is omega. This also contains some imprimitive groups. So they contain, your group has non-trivial G invariant partition, but with the property that the kernel of this homomorphism from G to G bar is equal to 1. And the purple part consists of non-quasi-primitive groups. So these are transitive groups with the property that there is a non-trivial normal subgroup that is intransitive. So this is how I like to categorize the transitive groups in this case, and we are going to see each of these cases one by one now. So we start with the primitive case first. So how did we deal with the primitive case? So we used the so-called no homomorphism lemma. This lemma basically says that if you have two graphs X and Y, if Y is a vertex transitive graph and there is a graph homomorphism from X and Y, then you have this inequality here. This was proved by Albertson and Collins in the late 80s, I think. And it's not hard to show that if you're given a transitive group and a transitive subgroup H, then your intersection density, the relation between the intersection density of G and H is the following. So the intersection density of the smaller group is an upper bound on the intersection density of the larger group. But this only happens for transitive groups, transitive subgroups, sorry. So now, if you look at a primitive group of degree 3 times p, then they're either two transitive, but this case is already done by Mars, Meagher, and Tep, so all of these have the EKR property. And the ones that are not too transitive, we call them simply primitive. So how do we proceed from here? So we look at the SOCL of the group. So the SOCL is the subgroup generated by all minimal normal subgroup of G. This happens to be a normal subgroup which sits in a primitive group. So this has to be a transitive group in this case, in the primitive case. And using the previous corollary, it's not hard to show to see that you have this. So the intersection density of your simply primitive group G is at most the intersection density of its SOCL. And basically using a lot of some heavy machinery in algebraic graph theory, we are able to show that, in fact, for all of these simply primitive groups of degree 3p, the intersection density of the SOCL is equal to 1. And the groups that we had to work with are the following, these 7 groups. I think one can even do this on the computer. Okay, so this takes care of the first case. For the primitive case, all of them have intersection density equal to 1. Okay, so I'm going to skip these two, but what about the imprimitive case now? So let G be an imprimitive group of degree 3p. So imprimitive again means that it has a non-trivial G-invariant partition of omega. And Marušić in 2021 showed that, in fact, if you have a block of size p, so if you have a G-invariant partition where the parts are of size p, then your intersection density has to be equal to 1. If you have more than one non-trivial G-invariant partition, then I was able to show in 2021 that your intersection density has to be equal to 1. And so the only case that we care about really are the imprimitive groups with a unique non-trivial G-invariant partition where each block has size 3. So in other words, you have p blocks and each of them has size 3. So let us consider a transitive group like that. So this script B here is my only G-invariant partition, and each block has to look like this. So let G bar be the induced action of G on this script B. And it's not hard to see that the induced action G bar is in fact a transitive group of degree P in this case. So we'll see later that this is important. We can use some very strong result on this. And let this be the kernel of the canonical epimorphism from G to G bar, which sends a group element G here to the element in G bar that corresponds to the action on these blocks. And using the fact that we have a unique G-invariant partition, it's not hard to show that the kernel of this homomorphism is equal to 1 implies that your group is quasi-primitive, and if it's not 1, then it is a genuinely imprimitive group. So there is a non-trivial normal subgroup inside that is non-trivial. So let us start with the first case, so the quasi-primitive case. So the kernel is equal to 1. Using the first isomorphism theorem, it's not hard to show that G has to be isomorphic to G bar. And well, now we use the classification of the transitive groups of prime degrees. So the sockles of such group is classified, and they are one of these 7 rows here. So basically what happens here is that since G bar has degree P, it is transitive of degree P, and this G here is transitive of degree 3P, and they're isomorphic. So in fact, your group G has 2 faithful actions of degree 3P and P. And it's not hard to show that, in fact, the only case where this is possible is row 6. So this basically takes care of the second part of the theorem, which says that G is an almost simple group that contains PSL and Q. So this is the proof of that second part. And the most interesting part now is the third case, the non-quasi-primitive case. So in this case, your kernel is not equal to 1. So this means that there is, well, the kernel itself is a normal subgroup that is intransitive. So Angelo Biazza, Rogaye Maleki, and I showed the following. So since your kernel is non-trivial, we let N be a minimal normal subgroup of G that is contained in the kernel. And if this N is an abelian group, then we showed that it has to be an elementary abelian 3 group. If it is non-abelian, then we constructed a certain clique of size 3 times P inside. So using the clique-co-clique bound, we showed that the intersection density has to be equal to 1 as well. And if N is abelian and the kernel contains a derangement, then we constructed a clique of size 3P again, and this makes the intersection density of the group equal to 1. So the only case that matters for this part is, well, so if you want your intersection density to be strictly larger than 1, then any minimal normal subgroup N that is contained in the kernel has to be an abelian group, and the kernel cannot contain a derangement, so it is a derangement-free subgroup. And now going back to G bar is a transitive group of degree P, and using a famous theorem of Burnside, such a group is either a subgroup of AGL1P or it is a 2-transitive group. So we consider these 2 cases now. So if G bar is a subgroup of AGL1P, then G bar is a Frobenius group, in fact. So it has to look as follows. So a semi-direct product of the subgroup generated by alpha and a certain beta. And this is isomorphic, in fact, to a cyclic group CP and the semi-direct product of that with CD, where D divides P minus 1. And your beta fixes, we can assume this, so it fixes the block B1 without loss of generality. And D here is the order of beta. So if you are in this setup, then it's not hard to show that your group G, in fact, has to look like this. So it is the semi-direct product of the kernel with a cyclic group generated by A, and that semi-direct product with a cyclic group generated by B. A and B here are respectively elements that are mapped to these elements here, so alpha and beta. And by analyzing the number of fixed points of B on this B1, so what you note here is that this beta fixes B1 and B is mapped to this beta. So B in fact has to fix P1 setwise. So by analyzing the number of fixed points of this P on P1 and the existence of involutions in the kernel, we concluded the following about the intersection density of these transitive groups. So whenever your kernel has no involution, then these are the possibilities. So the intersection density is equal to the maximum of 1 and 3 over t if the number of fixed points of B on B1 is 0 or 3. If the number of fixed point is equal to 1, then we also distinguish two cases depending on the order of the parity of the order of beta. So if the order of beta, which is in fact d here, is an odd number, then this is the intersection density. And if it's an even number, then this is the intersection density. And if the kernel has an involution, then basically we can discard these two cases by multiplying with an involution from the kernel, and this is the only possibility. So the intersection density of your group G, which is again equal to this GAB, is the maximum of 1 or 3 over d. And here, what we did is, how did we prove this? So we first showed that in the first case, in the case here, the derangement graph, in fact, is a lexicographic product of a certain graph and an empty graph. And from here, we could derive all of these using the no-homomorphism lemma, basically. And in general, what happens is that if G bar is a subgroup of AGL1P, then the question of Karen-Mar, in fact, is correct. So the intersection density of your group G is one of these three numbers. So now if you go back here, so these are the subgroups of AGL1P. And now we need to consider the subgroups of, well, the ones that are too transitive. So now the kernel is not equal to 1 and G bar is transitive. So basically, the only cases here are the following. So either you are an almost simple group. So in other words, there is a unique minimal normal subgroup inside that is, well, a non-abelian simple group, in fact. And G bar is equal to AGL1P itself. So these are, again, all the possibilities. G bar, in this case, it's not hard to show that this has intersection density equal to 1. But for the almost simple ones, we had to be a bit careful. So these are all the almost simple groups of degree P. And what we did is the following. So in G bar, you look at a P-Silo subgroup. Let P be a P-Silo subgroup. Then since G bar is of prime degree equal to P, a Silo P subgroup inside has to be cyclic. And it is in fact self-normalizing if and only if G bar itself is equal to P, which is your cyclic group. And since G bar is too transitive, the normalizer of the Silo P subgroup is never equal to just P in this case, so not self-normalizing. So this is the semi-direct product of P and Q, which is isomorphic to the semi-direct product of CP and CD. And what we do is we look at this homomorphism. If you look at the normalizer of your Silo P subgroup, this sits in G bar. And if you look at the pre-image of that, let us call that M. And the pre-image of this is transitive, and it has the property that M bar, the induced action, is a subgroup of AGL1P. So here we can use the result that I proved earlier. So for row 1 up to 5, basically everything goes well because D is greater or equal to 3. And it can be shown that the intersection density of M is the maximum of 1 or 3 over D. So in other words, the intersection density here is always 1. And using the no homomorphism lemma again, we were able to show that the intersection density of the group G, in fact, is equal to 1. The problematic case is row 6, whose circle is PSLNQ. So a CLOP subgroup in this case, since this has degree P, this is going to be a single cycle in PSLNQ. So a regular subgroup in PSLNQ. The normalizer of a single cycle in PSLNQ is a Frobenius group. And this happens if and only if n is equal to 2 or n is an odd prime. This was proved in the 70s. And basically what we do is we use a similar argument to what we had here. So you look at the pre-image of the normalizer of your single cycle. That gives you a group M, and you get an upper bound on the intersection density of G from that. So when n is an odd prime, everything works well because the intersection density of M again is equal to 1. But when n is equal to 2, this becomes a problem since your P, it is of this form. So P is Q plus 1, but P is also an odd prime. So this P here has to be a Fermat prime in this case. And the only thing really that we could do here is just give an upper bound, 3/2. But we think that the intersection density of such of this group G here is equal to 1. And this takes care of the last case of the theorem. And these are some open questions. So for the quasi-primitive case, we are thinking that the intersection density, in fact, is equal to 1. For the non-quasi-primitive case, we are not sure yet, but one has to study this group at least. So G bar is in primitive, the kernel is not 1, and G bar is equal to PSL2 Q. This is basically from this case where n is equal to 2 here. And another question is, can we do something similar for arbitrary Q? So here my Q is equal to 3, but is it possible to do something like this, at least for the non-quasi-primitive groups of degree PQ, where P and Q are distinct odd primes? And this is basically what I wanted to talk to you about today. Thank you.
Can I ask a question?
Sure.
First of all, that's great. I'm glad my wild conjecture was true-ish. What are your thoughts about arbitrary P's and Q's? What do you think would happen?
I think if you look at this, probably I think it will depend on the normalizer of this CLOP subgroup in the case where the kernel is not equal to 1 and your G bar is a subgroup of AGL1P. I think you'll get fractions in this case. When it is primitive, I'm sure that it might be equal to, all of them might be equal to 1. When it is quasi-primitive, I think it might also be equal to 1, but the non-quasi-primitive case, I think it depends on that G bar being a subgroup of AGL1P. And so I think it depends on the normalizer of this CLOP subgroup. I think. So I think maybe in general, it looks like 1 and I don't know, Q divided by something, Q divided by K, where K is like the order of something like this. It might look like that.
It's interesting. I have no idea.
Yeah.
Any other questions?
What are sort of the first open cases? I know I should be able to figure it out from what you've written here, but
I think this one probably is the hardest in this case. because the group G and G bar, they're isomorphic, and I don't know if one can use character theory or something like that to deal with this, but I think this might be the hardest.
But what would the values of Q be? Would they be big numbers?
These ones, I think, yeah, I think they might be big, yeah.
Good, good.
Yeah. I think this one probably is the hardest part here, since it's just weird to have a group that has well, like G is of degree PQ and G bar is of degree P, but the one G bar has naturally the EKR property, since well, it's of prime degree, but you can't use that to bound the intersection density of G. So I don't know, maybe that is something worth to investigate at least.
Can you give a bound on the size of the intersection density? Like here, the upper bound would be 3, but do you think there's any hope of reasonable upper bounds?
I'm not sure. I think probably one has to, well, I'm not sure. I think for the quasi-primitive case, I have no idea.
Okay.
But at least so far, all of the cases that I checked on the computer, they all have intersection density 1, but I think it just grows too quick.
Okay. Thank you.
Yeah.